These are the two broad categories of machine learning that we have. We have something called supervised learning and we have something called unsupervised learning. Broadly, this is how we can classify the two different forms of machine learning. We can call it supervised learning. What is supervised learning? Supervised learning is that kind of machine learning where the outputs or labels are defined. I mean, if you relate to it, this is pretty much what we talked about until now. Until now, all the examples I took, Google Photos, the XY example, the fruits classification example that I discussed, how a kid learns from lots and lots of examples of fruits. If you see in all these examples, the output is known. You are explicitly providing the outputs. You're explicitly providing information about the why. So you're explicitly telling the machine that, okay, the why is this. This is what the output is. The output is explicitly given. So the input is this, and the output is also explicitly given. And that's the way how we understand the idea of you know supervised learning. Outputs are defined. What is unsupervised learning? The outputs are not defined. But this is for a later conversation. We will come to this conversation later. What happens and how it relates to machine learning. But this is typically the clustering form of problems that we will discuss later on, where oftentimes the labels are not required. If you're doing something like a customer segmentation, so you don't need to know the labels. You just need to know the information about the customers. Imagine Amazon. So you're shopping on Amazon, and Amazon is constantly capturing data about, how many orders you're placing, what is the value of orders you're placing, and all this stuff. Okay, so Amazon is constantly sharing information about your orders, how many orders you placed, what value of orders you placed, and so on and so forth. So that is the whole idea, right? So that's the idea of what we refer to as a clustering kind of problem, where the rules are not defined. But this is where the traditional supervised learning rules are defined. You know explicitly what the rules are, and I'm sorry, the labels are defined. I mean to say the outputs or labels are defined. So you know explicitly what the outputs are, because if you don't know the outputs, then you cannot learn, right? The learning happens only if you know the inputs and the outputs. So the outputs are explicitly given in supervised learning, and that's why we call it supervised. Supervised, the name also suggests that somebody is supervising the machine. The machine is not learning by itself, but somebody is supervising, somebody is guiding it. There's a supervisor who is guiding the machine to learn, just like how a teacher guides a small kid to learn. You're guiding it, you're teaching it. Okay, these are apples and these are guavas, right? And there are two specific forms of supervised learning. One is called regression and one is called classification. Okay, so this is the whole stack. This is the whole stack. So supervised outputs are labels, outputs are defined, and there are two forms of it. One is regression and one is classification. So regression is that kind of problem where you're trying to predict a numerical output. Okay, so this is a numerical output that we are trying to predict. So examples could be, you are trying to predict the sales of a company. Okay, so say typical sales prediction, weather forecasting. Okay, so if you're looking at some games or some, let's say the game of cricket, okay, you're trying to predict how many runs will be scored, how many sixes will be hit. So that's typically a regression problem, because the output that you're trying to predict is a number. But there could also be some examples of classification problems. So what could be some examples of classification problems? Well, where the output is not a number, it's a categorical output that you're trying to predict. Okay, so it could be something like you're predicting that, okay, uh, based on the features of a person, you are trying to predict, will the person have a disease or not? Yes, no. You're trying to make a numerical prediction. So, will the person have a disease or will the person not have a disease? So that is how we refer to a classification problem. Or you can look at a typical network intrusion detection, a big part of what we do for the networking devices. Okay, so you have got lots of networking devices, and there are algorithms that are built in where different parameters of the network are monitored, and based on the different parameters of the network, the models are trying to classify that, is it a threat, is it not a threat. So the output is going to be something like, something like a category, or something like a yes no kind of a prediction. So that's the way how we can understand the classification problem. Just to relate to this a little better, just to relate to this particular idea a little better, what exactly, and maybe think of this in a bit of a better way. How can we think of regression and classification in a bit of a better way? Let's see that in action. So we have I was taking the example of, let's say, sales forecasting, or let's say network intrusion detection. So along the X, we have this is the input, right? So this is the input, and this is the output. So what we have here are lots of features, right? So the output will be either yes or no, and these are the features, right? So X1, X2, X3. These are all the different network parameters at a particular given point in time. There are, let's say, hundreds of parameters. So these are like individual features: X1, X2, X3, X4, X5, so and so forth. So these are all the features we have. And inputs are often called features, right? You'll oftentimes hear me use these terms interchangeably. I'll call them inputs or features, right? So oftentimes they're called inputs or features, and outputs are often called labels. There are other different terms that get used often. So inputs are called features, attributes. Outputs are called labels, dependent variables, dependent variables, and all that. But usually these are the two most common terms that are used. You call them inputs or X's, or outputs or Y's, or features and labels. So these are the different terminologies that get used. And what we again do as part of machine learning is, let's say if I want to build a kind of a intrusion detection model, I will collect a lot of historical data, right? I will collect a lot of historical data from my networking devices, and I will see, based in of the last 2 years, okay, in the pattern that is observed over the last 2 years, we are observing what happened. Okay, so whenever the network parameters were like this, intrusion threat was yes, and whenever the network parameters were like this, the threat is no. Okay, whenever the network parameters were like this, the threat is yes. And whenever the network parameters were like this, the threat is yes. So somebody will be labeling the data. Somebody will look at the historical data, and they will study the network configurations at that point in time. And based on that, they will say that, okay, when the network parameters were like this, that was classified as a threat. Our security team flagged it as a risk. But whenever the patterns were like this, the security team did nothing. You will have this kind of a data. This is like the XY combination. And with this, you will train a model. You will learn the pattern, you will design the rules, and you will have a working model. And next time you deploy that model, now you deploy that model, this model will run in production, live, real time, monitoring the organization's network intrusion detection things, right? Uh, and, and and next time there is a new, every second or every real time it is monitoring the network parameters, and next time it gets a new set of network parameter. This is like the X new. It will simply feed that to the model. Model.predict will happen, and you will get the predicted Y. So this is the way how you can think of machine learning. Use the historical data, learn the patterns, learn the association between the inputs and the outputs, and next time you get a new input, you use that to predict what is the corresponding output going to be. That's the way to look at it. And obviously, the more data you have, the more variety of data you have, the better the quality of your model. So this is how you can relate to a variety of use cases. Now you can even think of it in the context of a different kind of problem. Let's say a health data set. This was classification, by the way, because the output was categorical. It was not a number, right? You can also think from a regression point of view. Now, what could be a regression kind of a use case? Let's say from a finance perspective, a very good use case will be uh, loan interest prediction, something like that. Okay, you're looking at a fintech company, and the company will look at the different parameters of the applicant based on your loan history, your credit score, how frequently you're able to repay your loans. We look at your different parameters, and based on that, we will predict what is your overall interest, what is the interest we will charge you. Because usually risky borrowers are charged higher interest, and less risky borrowers, good premium borrowers, are charged lower interest, because they have they are more likely to repay the loans, right? So if you think about it, again, the data would be somewhat like this. You will have some inputs, you will have some outputs, right? The only difference is the output will be a number. You will have a lot of historical data that, okay, borrowers like this were charged this much interest. Borrowers like this were charged this much interest. Borrowers like this were charged this much interest. You will have a lot of historical data. And based on that, you will build a model. And next time there is a new applicant, you will do a model dot predict and predict what the interest rate for that new applicant will be. So that's the way how we can think of what's going on behind the scenes and how we actually frame a machine learning problem. Okay, and if you think about it, these are things that you cannot do using rules, especially for something as complex as loan prediction or health classification. You're looking at the different attributes of a person. and trying to predict whether that person has some disease or not. It's a very difficult problem. You cannot just identify a set of rules and say that, if your blood pressure is this, if your this is this, then you're diabetic, else you're not. It's very hard to do that because oftentimes these patterns keep changing, and oftentimes the dynamics between the features are so much that you cannot represent them using simple rules. So what I'm getting at is, in many of these real world scenarios, the rules are very hard. They're very hard for a human being to define, and which is why we resort to machine learning. We want a machine to instead design the rules for us. We want a machine to learn that particular input output relationship for us.